All right, grade 12s, now that we learned about electric fields and electric potential and electric potential energy, we're getting ready to figure out why do we get zapped when we touch two terminals of a car battery, a very life hazardous situation. Okay, so hopefully in the next few videos we can see how this didn't really happen, it's a prank, but we can see how that can be a potentially dangerous situation and understand why that occurs. All right, so for today's lesson, what we want to do is we want to understand how electrical potential difference is set up across conductors. Okay, when we hook up a battery up to a wire, why is an electrical potential difference set up? And why does that electrical potential difference lead to something called an electrical current? Okay, so we're going to understand the definition of electrical current. And then we're going to understand why when we plug a wire to the terminals of a battery, the wire gets hot. Why do your devices, like your computer, your battery charger, why do they get hot when they're plugged in? Okay, these are the three things we're going to learn just in today's little video. So first of all, in order to understand that, we need to figure out how a battery creates potential difference. Okay, up to now, we've been charging metals with electrons or taking electrons away and then creating electric fields by creating charged objects. It'd be very strange if I had to rub fur on plastic to charge my car every morning and then get it going. So what we have are chemical batteries that store electrical potential energy. And how they work, this is a common 12-volt battery. It's a lithium battery. It's probably not in your car. It's probably in an electric car. Okay, it's a 12-volt battery. It has 10 amp hours. If you want, you can research what that means. But that tells me how much charge is stored in the terminals of a battery. Okay, and that battery transforms chemical energy, the reaction of the lithium in the battery, to electrical potential energy. So that must mean that the chemical reaction inside of that battery moves charge. Okay, so there's a chemical reaction that moves charge to one side. I got a plus side of the battery, that's plus, and this is minus. So what had to happen is somehow all the plus charge went to that side of the battery and all the negative charge went to that side of the battery. And that's mediated by a chemical reaction inside what's called a voltaic cell. For physics, we don't really need to know the in and out of that chemical reaction. All we need to know is that the reaction does work. Okay, so the chemical energy did work to move the charges. And every time I move a positive charge to one side, it's going to take more work to move another positive charge. So it's a pump. It pumped a lot of charge and primed it on one side of the battery, okay, creating a lot of electrical potential energy. And what often textbooks and videos would equate that to is like our old roller coaster phenomenon. Okay, so the roller coaster that is at the bottom of a hill is going to have low potential energy. Okay, in order to get that roller coaster primed and put to the top of the hill, somebody had to do work to push it. Okay, and it'd be really difficult to push that, let's say 100 meters up, and let's say that roller coaster is 1 ton. Okay, that would be a heavy roller coaster to push up 100 meters. It would take a lot of people, not just one person, to move that roller coaster uphill. And in a battery, you have a chemical reaction that's pumping it. Instead of the roller coaster, what you have is charge. Okay, so I got a positive charge. And the chemical reaction is pushing that positive charge uphill to high potential energy. Okay, and it's storing that high potential energy. So all that positive charge is going to get stored at the top. And it'll sit there until all of a sudden somebody builds a ramp to allow those charges to flow back down to low potential energy. Okay, and when it does that, it will release energy. Okay, so that's kind of how a battery works. Okay, so battery creates potential difference when I connect that battery to, let's just erase this. Okay, so when I connect that battery to something, let's just imagine I have a battery. This is the positive terminal of my battery. That's the negative terminal of the battery. If I connect it just to two metal plates, okay, what's going to happen is that the electrons in this plate are going to sense that positive charge and they're going to move in that direction, leaving a highly positively charged plate on this side. And then on this side, I have excess electrons coming from here, moving into that, creating a highly negative charged plate. So if I had a potential difference of 12 volts in the battery, what would end up happening is I'd have charges migrating so that I would have a 12-volt potential difference across those two plates. And of course, this is the electric field that is generated between those plates, like we learned in the electric field section. And 12 volts means that a charge is going to have 12 joules per coulomb of energy from that side of the plate to that side of the plate. Okay, so if it moves from one side to the other, it would release 12 joules of energy per coulomb of charge that flows, and that's what a battery does. So when you connect a battery into a circuit to conductors, and if the conductors are separated a little bit, it would create a potential difference across those conductors. Okay, even if I connected a battery to just a wire, a closed wire, okay, what would if I would just zoom in and I would look at that wire over here, okay, that side of the wire would be positive, that side of the wire would be negative, and across that wire would be a potential difference of 12 volts, even though the wire is connected. Okay, so from here to here, I would have a potential difference of 12 volts, okay, and the charges inside the wire would feel that potential difference. They would see this electric field, and the charges would be forced to move because of that potential difference. Okay, it's something that we practiced in the last video. So just to summarize, the chemical reaction inside of the battery creates that positive and negative charge in the battery, which then can create an electric field in conductors that are attached to the battery, okay, causing charges to move. So how does a battery cause the charge to move? Just as I described, it creates an electric field. So if I have highly positive charge set up in one side of the battery, and it's not allowed to flow back inside, here's like a membrane that doesn't allow those charges to move back. Okay, when I connect that battery to a wire, the wire is going to have an electric field set up in it. Okay, so this side is going to be a negative side, that side is going to be a positive side. Okay, and according to our electric field, the electric field is the flow of positive. So my electric field, okay, would have a lot of positive charge on this side, negative charge on this side, and I would have that arrows pushing positive charge in that direction and negative charge in that direction to kind of counterbalance. So if I connect a battery to a conductor, okay, a conductor, remember, like metal, has free electrons. Okay, the electrons are like a cloud around that metal. Okay, they're freely moving. So if I connect a battery, this is my plus side, okay, and this is my negative side. If I connect a battery to that metal, that electron cloud is going to move. So the negative charge of the electron cloud is going to be moving towards the positive side. So I would start to see that electron cloud move. Okay, and this side of the metal would then become positive, so the electrons on this side would move. Okay, so the potential difference that the battery has once it's connected can create an electric field in the entire metal that causes these electron clouds to move. But very, very important, in physics, we don't talk about the movement of electrons. We didn't know about it to begin with. Current is the flow of positive charge. Okay, in physics. So in this case, the current is going to be positive charge flowing. Even though positive charge doesn't really flow, the electrons flow, in physics we look at current as the flow of positive charge. So if I was to draw the current, let's just change the color here. If I was to draw the current, this is the direction of the electron flow, but that would be the direction of current. In physics, because it's the flow of positive charge, which is kind of odd, all right, because the positive charge wouldn't flow, but that would be the direction of the current. So once I set up an electric field across a conductor, the electrons get moved, but physics says that it's the opposite direction. It's moving the positive charge in that circuit. So the battery, in a nutshell, creates an electric field that causes the movement of charge. What is the definition of electric current? Well, electric current is going to be the actual flow of charge. And flow is not a really good term. It's actually the rate of charge movement. Okay, which is measured in coulombs per second, which is equal to 1 ampere. Okay, the symbol for that is an A. So 1 ampere is the measurement for current, And 1 ampere would be equal to 1 coulomb of charge, which is a lot of charge, flowing through a circuit in 1 second. So if I was standing right here and I'm counting all the charges that flew by me in 1 second, and I multiplied them by the elementary charge, I'd be able to calculate the total number of coulombs that flew by that point in 1 second. Okay, and if I put that ratio together, that would give me the unit ampere, and that's current. So the question that I have is, what limits current? An ampere is common in a lot of your electrical devices, and an ampere is a huge current. 1 coulomb of charge per second is a very huge current. Okay, some of your devices, and of course, like if your charges, if you look at it, have 5 amps. 5 amps is 5 coulombs of charge flowing through that per second. That's a very dangerous device because that's a lot of charge flowing through you if you put your fingers into it in 1 second. Okay, so now you know how to read your devices. If they're ampere or above ampere, they have a large amount of current flowing through them. So what limits the amount of current flowing through a conductor? Well, what limits it is resistance. Okay, so inside the wire we have a bunch of atoms. Okay, and when I connect that wire to a battery, I'm going to be moving electrons, but as the electrons move, they bump into the atoms. They bump into the nucleus of the atoms, and every time they bump, they jiggle those atoms. Okay, so the more congested it is, the more atoms they're bumping into, the more lattice atoms they're bumping into, the more that electron gets bounced around, and the more those atoms start to jiggle. Okay, those collisions between the electrons and lattice atoms is called resistance. Okay, the more resistance, the more they're bumping around. The more they bump around, the more kinetic energy these atoms get. Okay, and if I increase the kinetic energy of those atoms, I'm going to cause a raise in temperature. Okay, so the more bumping around, the more resistance I have, the slower that current is going to go through, and the more bumping I'm going to get, the more collisions I'm going to get with those atoms, which cause them to move around, causing a raise in temperature. So that would explain why wires get hot when currents are flowing through them. Okay, but most important, the more resistance a wire has, okay, the more heat can be developed if a current flows through it. However, if I have a lot of resistance, I might not be even able to get a current going through it because those electrons, just as soon as they start moving, keep bumping into atoms. So I might not be able to see a current flowing through if I have too much resistance. And that's going to be the topic of the next video when we talk about the relationship between voltage, resistance, and current.